So now we are in the middle of learning about Rödl Nibble. So I will mention about why we call this Rödl Nibble later. And in proving that later, we will use the second moment method. So our goal is again proving this theorem. So when we have a K uniform hypergraph, K is at least 2, it's an integer. And if this D is sufficiently large and delta is sufficiently small compared to the given epsilon and given epsilon and K. If H is a K uniform hypergraph, which is almost regular, and the degree is very close to D, this large number, and its codegree, for given two vertices, the number of edges that contains all of them, contains both of them, is the codegree of these two vertex, and then we consider the maximum codegree out of all the pairs. In particular, if you have a two uniform graph, which is a graph which is simple, then codegree is at most 1. Anyway, this is much smaller than compared to the degree. Then we can find the matching, which is almost perfect. This is a K uniform hypergraph, so it covers at least 1 minus epsilon times n many vertices. So this is what we want to prove. One of the applications is into this NLK block design. So when we say NLK block design, it's a collection of sets of size L, which satisfy the following condition. For any set K of size K, capital K of size small k, there exists exactly one set of size L in this collection containing this. So for example, if you consider N32 block design, it's called the Steiner triple system. So what it means is that for any pair, there exists one set of size 3, which exactly covers this one. So this is actually equivalent of saying that if you have a complete graph from Kn, you decompose into triangles. So here decompose means edge decompose. So we want to partition this into edges such that each of the edges form a triangle. This consists of 3 edges which forming triangle, this consists of 3 edges which forming triangle, and then no edge is used twice, and then every edge is used exactly once. So can we partition it? Then for this triangle, we just consider a set of 3 vertices. Then as each edge is belonging to exactly one of them, that means each pair here of the vertices belong to exactly one set of size 3. So these two are the same thing. Then one typical question is that does N32 block design exist? If you consider that if you have complete graph on n vertices, it has n choose 2 edges. So first, if we want to be able to partition it into triangles, then 3 must divide n choose 2. So that's one necessary condition. And also, if you have, say, 6 vertices, then every vertex has degree 5 in Kn. And some triangle uses 2 edges here, and some triangle uses no edges incident to this vertex. and some triangle uses two edges incident to here. So that means if this vertex has odd degree, then there is no way that you can cover you can use all the edges by edge disjoint triangles. So this implies no triangle decomposition. So 2 has to divide n minus 1. This actually is equivalent to saying that the n is 1 or 3 modulo 6. So this condition is a necessary condition for the existence of N32 block design. In other words, the triangle decomposition of complete graph on n vertices. And it's actually known that Kn decomposes into triangles if and only if n is 1 or 3 modulo 6. So this is not only a necessary condition, but also sufficient condition. In general, I mean, if you consider N, L, K block design, it's actually same as a complete graph, complete K uniform hypergraph on L vertices decomposition of complete K uniform hypergraph on n vertices. So there are n vertices, and then this counts all sets of size K. And then what's this? That's a complete graph on L vertices. There are L vertices, and every K tuple forms a hyperedge. So you choose L set here, then that covers that uses all the sets of size K inside of them. And we delete them, and then we choose another L set, another L set, another L set, another L set. So each of this forms a copy of KLK, and we want to make sure that every edge here, every set of size K here belong to exactly one such copy. So that's same as NLK block design. It's the same logic as as the equivalence of these two. So we can ask whether this holds. Again, similarly as before, we can actually check some necessary divisibility condition. And it's been conjectured that this exists, NLK block design exists if and only if the divisibility condition holds. It's been open for more than 100 years until recently. Kibash proved this for sufficiently large n. So this direction is easy, but the necessary direction is this one. So this holds if n is sufficiently large. Compared to LK. However, before Kibash proved this, in 1963, Eldwish and Hanani conjectured that ask whether the approximate version of this holds, meaning that for any epsilon, if n is asked if n is sufficiently large, then epsilon approximate decomposition of this K uniform complete graph on n vertices into copies of L vertex, K uniform complete graph, complete hypergraph. So here the epsilon approximate decomposition of Kn into say copies of Kl is a collection of H disjoint copies of KL in Kn, which covers not all. So we ensure H disjointness. That means every set of size K belongs to at most one set of size L. But we are actually allowing some K set, some set of size K to be not covered. But most of them should be covered. O minus epsilon fraction of the H's in Kn. So we call that epsilon approximate decomposition. Then, this conjecture was proved by Rödl. So for KL, say epsilon, if n is sufficiently large, then epsilon approximate decomposition of Kn into KL exists. So we use this Pippinger's theorem to prove this. So historically, the order is the other way around. So Rödl actually proved this using Rödl-Nibble, and whatever that method is, I will show you later. Rödl proved this using Rödl-Nibble, and then later Pippinger noticed that what essentially is going on in the Rödl's proof is, can be captured by using this language of hypergraph matching. And formulated the theorem regarding hypergraph matching in that way. So let R be the, how do we do it? L choose K. And we consider a auxiliary hypergraph H. H be the R graph, R uniform hypergraph, whose vertex set, so vertices are all the sets of size K in bracket n. So in other words, vertex set of H is sets of size K in bracket n, and whose H's are all L choose K sets that lie in an L set. So H set of H is the, how do we do it? The collection of all K set in L, where it has size K, for every L set so each of these is an edge. Then first H is regular. Each vertex in of H has how much degree? Degree is D, say, which is n minus k, choose L minus k. So you have k sets. The number of sets of size L which contains this is, you have to choose L minus k other vertices. Not vertices, other numbers in bracket and here. So that's the degree. And every two distinct vertices, say k and k prime of BH, so which is actually size n, choose k, has co-degree. So its co-degree is actually n minus size of k union k prime minus L minus k union k prime. And here these two are distinct. So k union k prime is at least has size k plus 1. So this is at most n minus k minus 1, L minus k minus 1, which is Rödl of D. So more precisely, it's big O of 1 over n times D. So what do we know? We let n be sufficiently large. So on this Pippinger-Spencer, let's say we fix these two. Then we have this D and delta. So n is sufficiently large, so 1 over D is sufficiently small. And then we also let n be sufficiently small, so we can actually ensure that the n is 1 over n is smaller than delta there. Then this is smaller than delta D, and this is D with this choice. And they are large enough, and this is small enough compared to the capital D. Thus, this theorem, Pippinger theorem, implies that H has a matching of size at least one minus epsilon times n choose k divided by L choose k. But what's this matching is? This matching is set of size L, which is disjoint in H, meaning that which does not share any k set in N. So they can actually intersect with a set of size less than k. They are still disjoint in H, but on this N, they could actually intersect because this is matching in H. So each of them is a copy of actually KL, K in this. This is not H. In here, each of the H in this matching is copy of this, and then they do not share any set of size K, and then it has this much size. So this yields an epsilon approximate decomposition of Kn into KL. Copies of KL. So this proves the Ehrlich-Hanani conjecture, which is proved by Rödl. Give me a moment. Wait. Why is it not moving? Sorry. So now what we want to do? We want to prove this Pippinger theorem, the theorem regarding hypergraph matching. So again, what it means is that if you are almost regular and small codegree, then you can find the matching of size, almost perfect matching. And how do we want to prove this? We want to prove this by using Rödl Nibble. So Nibble is like a small bite. So you have some cookie that you want to eat. Then you can just eat whole thing in one go, but Nibble is not that. Nibble is you eat small bite, and small bite, small bite, small bite, small bite, and small bite until you eat all. So so now what we want to do is that you have a hypergraph H, and you want to find the matching. And how do you want to do it? You take some small number of H disjoint matching, and then you take it out. And then you see the remaining, vertices, and then hypergraph it induces. And there you also take a small fraction of H disjoint 1, and then consider the hypergraph remaining here, and you repeat. You take it small by small. So that's why it's called Nibble. So we want to show that H, which is say H0, has large matching, almost perfect matching. So that's our goal. And what do we know? H0 is almost regular and small codegree. So what do? Is we have this H, and we choose some hypergraph H's uniformly at random, independently at random, not uniformly at random, but independently at random with certain probability P. Say P is alpha over D. Then we can actually show that the roughly alpha proportion of the vertices, of the edges are chosen. And say alpha and many vertices are occupied. And then because this is small, most of the edges are disjoint. So there could be some edges which are not disjoint, but we can just, throw away if small number and make sure that these are disjoint. And then you delete these edges. Delete these vertices. You take out these vertices, and then you recall these edges. Then, now you take the remaining vertices, and then, let's say H1 be this H0 on this, say, remaining vertices are V1. Of course, if there could be some edge which was lying in this manner, but after deletion, they are gone. So, then, now, what's the degree in here? Degree of the vertices here. Roughly, so it has this vertex is here, and then it has k minus 1 other vertices. And if at least one of them is included here, then this edge is no longer there. So this edge is still inside of this H1, means that each vertices were not included in this deleted set, say W. However, because these edges are randomly chosen with probability, say, P, then this has size alpha n. So each vertex is is roughly, chosen to be in W with roughly probability alpha. And this vertex, the other k minus 1 are surviving, meaning that it's not included in W with a probability roughly with this probability. If this vertex is already in there, then this H also survives with this probability. So initially the V has a degree roughly D, and then after this we can actually show that this is roughly 1 minus alpha times to the k minus 1 D. Meaning that this H1 is again almost regular. Its degree decays a bit faster than the size of vertices. Initially, n vertices become 1 minus alpha times n vertices in here. But the degree actually decays a bit more fast, but still we can show that this is almost regular. And also, we can show that H1 still has small codegree. Then again, this H1 satisfies two conditions of almost regularity and small codegree. Then you repeat. You randomly choose some vertices, and then again let this be W and throw it away. And then remaining one has H2. Again, H2, you can show that this is almost regular and have small codegree. You keep repeat this until the last, until you do this until you have a HS which has very small number of vertices, then which has a less than epsilon n vertices. Then you just throw the vertices away, and then you just collect all the edges you have collected so far. They form almost perfect matching. So that's roughly what we want to do. And while doing that, we have to show that we have to show several things. First is that if we randomly choose these edges, then indeed we actually delete the almost correct number of vertices. We have to show that one. And we have to also show that the remaining number of vertices is correct. And we have to also show that also these are mostly disjoint. After throwing away some chosen edges, we have to make sure that this is matching with the correct size. And then we also have to show that after each step, it is still almost regular. All of these are saying that they are all related to concentration. We have to show that the vertices have the degree which is very close to its expectation with high probability. And we have to show that the size of this set is very close to this correct number with high probability. And also the number of edges remaining, or number of edges which are disjoint, are very close to expectation, so that we actually get the correct collection with high probability. So that's what we will do in the next video.